we want to talk about something called stable matchings. So we're going to be looking for a matching, actually a perfect matching in a bipartite graph that satisfies these certain conditions, that it's stable. So let me define a few things here so we can actually talk about that more directly. Okay. So let's let G be a complete bipartite graph with classes A and B. We're going to call the class, let's actually do this, classes A, which are going to be called the men, and B, which are called the women. Okay. So this model we're using today is pretty outmoded. We're going to set up marriages between men and women here, and this traditional propose and reject algorithm. This model, though, is still pretty helpful for like imagining the problem here, because we'll often just refer directly to the men or the women in the algorithm. It's just easy to have like some designation for the classes here. Okay. All right, so we've got that bipartite graph. We got the men and the women, and then each man and each woman has a ranked list of the people in the opposite class there. Okay, so like the people they most prefer in a relationship or in a marriage. Okay, so each man A in A has a ranked list of the members, the vertices of B. And each woman, B and B, has ranked list of A. Okay, so each has this list of suitors ranked by preference. These lists are the lists of preferences, although we'll just refer to them as the lists. So these are the lists of preferences. That's the name we give to those two things. Okay, so now suppose we have a perfect matching M in G. So what does that mean? A perfect matching is a pairing of each man with one woman, right? It's just a matching of all the vertices of the graph. So you can think of it as a list of marriages. Okay, so we have a pair AB. So A is in A, B is in B, who are not matched. This is an easy place to make a mistake here. So I've got a man and a woman who are not married to each other, but they're in a situation where both of them prefer each other to their current partner. Okay, so they're both married to someone, but if they compare each other on the lists, each of their own lists, the person they're not married to in this pair here is higher ranked. Okay, this is like a bad situation, right, to be in this list of relationships. If you just play with the metaphor, obviously, but in these problems, this is important. Let me see here. Did I have the chat message here? Eric says it's getting a bit too real. It can be very real, yes. So let's see here. Such that, yeah, okay. So such that, and I'll use sometimes like this metaphorical language. So such that A prefers B to his current partner under M, right? We've arranged all these marriages in advance here, and A prefers B to his current partner, and B prefers A to hers. Okay, and I'll illustrate a few examples in a moment here. But this is, like I said, this is a bad situation. This pair is called an unstable pair. Okay, and remember, so what is prefers? This means that appears higher in ranked list, right? They each have that list of preferences. Okay, so yeah, this pair is an unstable pair. Right? I think you know why. Right? This is not a good situation. So these two people, at least according to their list, would be better off by leaving leaving each other, their current partners, and remarrying each other. So this is an unstable arrangement of marriages. We want to avoid this. Okay, so a perfect matching with no unstable pair, right? So if we can arrange the marriages and avoid this scenario, that's what we're trying to do here, right? We want to make everyone reasonably satisfied. Okay, at least people may have others like out there they're not married to who are ranked higher on their list, but those people prefer their current partner to that other person. So there'd be no reason to trade in this thing here. One party would never want to, at least one party of any unmarried pair would not want to change the situation they're in. Okay, it doesn't mean everyone's happy, but it means that there's no possible swaps to make. Okay, so perfect matching with no unstable pair is a stable matching. Okay, and so that's what we want to talk about, at least for the first half today, is how do we find stable matchings? Do stable matchings always exist, given a ranked list of preferences in a complete bipartite graph? So let's look at a couple examples. There is an example in the notes. There's a slight typo in it, so I'll just run through it here with the fixes, and I'll fix it in the notes as well. So let's say we have a list of men, A, B, and C, and women 1, 2, and 3. I know I named the set of men A and the set of women B, but I'm just using this for individuals at this moment here. And each one of these comes with an associated list. So A's preferences for women is 1, 2, 3, B's are 1, 3, 2, and C's are 2, 3, 1. Okay. These three lists are different. There's no requirement that they be different. A and B could have the exact same list of preferences among the women. That's certainly possible, but this example doesn't have this. And then one prefers ACB, BAC, and then CBA. And let's suppose we have the following arrangement. So those two are married, these two are married, these two are married. Okay. Now we want to ask, is this stable? Okay, that didn't change colors. Okay. So if we want to check if it's stable, we need to check whether there's an unstable pair or not. We need to rule out every possibility of an unstable pair. Now, remember, an unstable pair is a pair AB who are not matched to each other. They're people that would swap to get to a better relationship. So in principle, if you have like a really big bipartite graph, you're gonna have to check all the edges, all the non-edges, so all the things that are not matched. So there's a lot of things to check. Like even here, it's gonna be a headache, but fortunately we can rule out a couple things first. Can person A or person 1 ever be involved in an unstable pair? Right, Andy, can you say why? I see that you.
They're both matched with their best preference.
Yeah, exactly. Both A and 1 are matched with their best preference. So A would never have a reason to trade up, and neither would 1 ever. And they happen to be matched to each other. So at least when checking for unstable pairs here, I don't need to worry about anyone involved with A or 1. So it just makes my life a little easier in this specific instance here. So let's check, for instance, B and 3, right? Would B ever trade for 3? So B actually would prefer to be with 3. Everybody see that? 3 is higher on B's list than 2 is. But 3 is ranked with her highest ranked person, right? So, or at least what's important is she's ranked with someone higher than B. So B would like to trade to marry 3, but 3 wouldn't, okay? So that pair is not unstable, so it's not a problem. Okay, what about this one here? This pair here, B is with, 2 is with B, which is her highest ranked person, so she wouldn't trade either. I don't even need to examine C. It looks like C would prefer to trade. Okay, C would prefer to trade, but you have to have both sides in agreement to trade here. So this is stable, right? This matching is stable. No one would want to leave their partner. Well, some people may want to leave their partners. Let me be clear, right? But you have no two unmarried pair who would trade simultaneously. Okay. Let's see here. So I'm gonna keep the same list of preferences, but I want to draw another matching here. Okay, so just duplicate everything that's here on the left, and let's say we have the following matching instead. Those two are together, these two are together, and these two are together. Okay, so this is different from the previous. Again, these two are not going to be involved in an unstable pair because they're with their highest ranked people. But let's see about these ones here. So these two that are unmarried, yeah, and notice I never checked like this pair here. As I said, number one, A would never be involved in a unstable pair, so there's no reason to actually go ahead and check that. But in principle, I had to check those ones as well. Okay, so what about this? B is happy, right? B here is matched with his second highest ranked person, which is 3 instead of 2. So this is not an unstable pair because B doesn't want to trade up in this case. Before, B was happy to trade up here, but now B is happy to stay here. So that's not unstable. And then this one here too, I think it should be stable as well, because 3 is relatively unhappy because she'd rather marry C, but C is happy. C is matched to his highest ranked woman. Okay, so this is also stable. Is that okay? Everybody see that? This is a stable matching, so is that one there. What I want to emphasize here is that the same list of preferences may lead to different stable matchings. Okay, so there's more than one here. There's not like a unique stable matching necessarily. And then there, of course, are unstable marriages as well. This one here is going to be unstable. So these two and this one here. And just from the things we observed already, can someone tell me why this one's unstable? You don't even need to, I mean, you do need to examine, but we should be able to identify immediately why this one's unstable.
We have we have one element of each set that wants to trade.
Yeah, exactly, right? And we know that's this one right here, was 1 and A and 1, right? We already knew that in the previous ones here, they were in the best possible case, like their highest ranked people, they were married to each other. So if they're unmarried here, clearly they'd be better off, right? Like if we examine here, A is in this third model, A is matched with 2 and 1 is matched with B, but A prefers 1 to 2 and A prefers A to B. So both of them simultaneously, so the pair A1 is unstable. Okay, so this is not a stable matching. Okay. Same set of preferences. And then in principle, although we're going to rule it out shortly, in principle, I could give you some crazy list and there'd be no stable matching, right? I mean, in principle, like at the moment, we don't see that there should be a stable matching, right? It may be that every matching I come up with always has this pair that's unhappy, like this unmarried pair that could trade up. Okay, it's not clear how to get that. In this one here, I mean, one approach, and I don't know if you can actually prove it this way, but one approach is to look for unstable pairs, remarry, and then look again for stable pairs and try and remarry. But this could end up come in some kind of circular thing where we just keep having to trade forever and it doesn't halt. Okay, so I'll introduce a very simple algorithm here that will solve this problem. It'll find a stable matching for us and therefore prove that there always is a stable matching as well. And this algorithm is very easy to implement. It's very easy to describe here. And one of the reasons we keep this man-woman terminology here is it makes the algorithm pretty easy to describe as well. And actually, as pointed out in the graph theory book I used, is this algorithm is essentially how is like the idealized model for how men and women, or men proposed to women, 200 years ago. Like this was, and like when you watch Downton Abbey or stuff like that, like in that era, like this is how people imagine it. I don't know that actually is how things worked, but it's easy to visualize it here. Okay. And then I have a little bit of social commentary for you at the end as well that I think is pretty, well, I mean, yeah, it's pretty interesting. Okay, so we're going to do the following procedure iteratively. Okay, so what happens in the first step is at each day or each month or each time period in the algorithm, each man proposes to the highest ranked woman who hasn't yet rejected him. Okay, so iteratively do the following. It's just going to be a bunch of rounds until the algorithm terminates. At each step, I'm just going to call it a day. So say we're going to just do new marriage proposals every single day until we've solved this thing here. Okay. Each man proposes proposes to highest ranked woman. I mean, on his list, right? Each person has their own individual list. Who has not yet rejected him. We haven't said anything about what it means to be rejected. So on the first day, literally every man will propose to the highest person on his list, right? There's no rejections yet. By the way, the name of this algorithm is the propose and reject algorithm. All right, that's a nice name. All right, nice name. Okay, so each man proposes. That's like the first step. Now, women may get multiple proposals, or they may get no proposals, right? Or they could get one proposal. What the women do is, if they get multiple proposals, they reject everyone except for the highest ranked on their own list who proposed to them, right? Does that make sense? Like, if I'm proposed to by 3 men, I should reject the 2 lower than the top because there's no reason to marry them. I got a proposal already from that guy, and he's going to continue to propose to me because he's not, his, like, what's above me on his list has already rejected him. That's why he got to me. So that's the best I can hope for as of now, right? I may get a better proposal later, but so far that's the best, and I should keep with it. Okay, so now each woman rejects all but her highest ranked proposer. Okay, among the men. 2 things to observe. If only one man proposed to me, then I don't reject anyone. I just say maybe. Okay, yeah. So I don't accept that one though. I just say maybe. Okay, it says, let's say maybe to top ranked man. We don't really need this part here. This says maybe. There's one thing, and it's reject. But if I get 1 proposal, I don't reject him. If I get no proposals, I don't do anything. And if I get 10 proposals, I reject 9 people and say maybe to the one highest ranked person. That's the end of day 1. And this just repeats on the next day. So now some men have been rejected, and the next day starts, and each man now looks at their new list. Some people have been crossed off and reproposes. And you continue this until it stops, if it stops. We'll think about that in a moment here. Okay, so continues until each woman gets at most 1 proposal. In other words, no woman's able to reject that day, right? When you get to a point where no rejections happen, then there's no update to the lists, and so we have no choice but to stop. Otherwise, the algorithm would just keep doing the same thing every turn, okay? So no woman can reject. And then at this point, each woman accepts the 1 proposal that she has at that moment. And now each, let me just put that on a new line here. Each woman now marries the remaining proposer. If it exists, right? If it exists. We've clarified it's possible in principle that a woman doesn't get a proposal on a certain day there. Okay, actually, we'll rule this out quickly. All right, so this algorithm is quite straightforward, right? Each day, all the men propose to the highest ranked woman that's available to them, and men in principle get rejected in a day or they don't, right? Each woman's got their list of suitors, and she rejects everyone but the highest one. Okay, so she's keeping this like running total. This guy might win for a bunch of days, and then some other man eventually proposes to her that was higher ranked, and she says, oh, "Okay, you're gone now. I keep this higher ranked guy for from now on." So yes, Van, absolutely, yeah. So to be clear, a man may repeatedly keep proposing to a woman forever. Like in the example above, actually, I guess we could run the algorithm on this, but I haven't actually gone through it here. So on day 1, A is going to be proposing to 1 because that's his highest ranked. And let's see here, B will also propose to 1, and C will propose to 2. Okay, so after day 1, woman 1's going to say, well, I reject B, right? So he actually is going to cross that off of his list there. And let's see, 1 is going to tell A maybe, right? Because she got 2 proposals, so she doesn't stop. And we stop when at the same time for everyone, okay? And then what did we say? C proposed to 2, so 2 will also say maybe. So that's day 1. Not much happened. All right, day 2, A proposes to 1 again, B proposes to 3, and C proposes to 2. And then we actually stop, right? Because now A got 1 proposal. Sorry, 1 got 1 proposal, 2 got 1 proposal, which was C, and 3 got 1 proposal, which was B. So none of the women are able to reject. We haven't exhausted these lists at all. And that actually produces this matching here. Everyone see that's the one that we get out of it. We don't get this one here. It's not clear which one we get, but we get a stable one there. So it's a very simple algorithm there. Okay, so for instance, A just kept proposing to 1 here. And if we had a huge model here, A would actually propose to 1 the entire time because they're highest ranked with each other, right? It doesn't usually work out that way, right? Usually you end up marrying someone who's somewhere in the middle of your list because of the timing in which proposals happen and so on. Okay, so, whoa. So before we prove that this algorithm works, I want to mention something here. I don't want to go through all the details here, but there are different matching theorems that you can make for stable matchings, and you can describe them as man optimal or woman optimal. It takes a little bit of thought to figure out exactly what that means. What's interesting though is this algorithm, on the face of it, looks like it's woman optimal in a sense, right? It's like, look, woman's receiving the proposals, she can decide who to reject, and she can always take the best person, and it seems like she gets the best outcome here, possible. But it's actually counterintuitively the complete opposite. This is man optimal. So like this prefers the men. The men will get their best possible choices they could ever hope for under this algorithm. And the women will basically get the worst in some sense. I mean, they may get matched with the best person, but globally is the worst for them, which I think is pretty interesting because again, on the face of it, this looks fair. It looks good for the women, and it's just not. It's not only not, it's best for the men and simultaneously basically worst for the women. I think there's kind of a lot going on there with this. Like I said, this is a traditional way of doing marriages. It's not done like that anymore, obviously, for a number of reasons. A couple interesting things about it, though. This algorithm is used heavily in matching things up. This is how residents are assigned to hospitals after they graduate from med school. It's a little bit more global because you don't have 1 resident per med school, you have multiple, but you can make a richer version of this. And basically that's the way it goes. Med schools rank the potential residents, and the residents rank the med schools, and you run this algorithm, and you get matched that way. I had a student once tell me that actually this is how sororities decide sisters too. I think they're called sisters, right? The women who are going to join a sorority list their preferences by sorority, and the sororities do the same, and you run the propose and reject algorithm, and that's how you get matched up. So these are just 2 like, baby examples where it's used, but it's used in a lot of other places as well. This is an important, although very simple and in some ways obvious algorithm. I mean, it's not obvious that it works, but it's a reasonable thing to try, right? I mean, it's like it might produce a stable matching. Okay, so that's the proof. So we're not going to be able to see this, so try and keep it in your mind. Let me just read through it one more time, right? Each day men propose to the highest ranked person that's available, and the women, so there's just 2 steps. Men propose, and then women reject, right? They reject everyone but the highest ranked suitor. And the point is, it ends in a state. We'll never get an unstable pair in this. All right, so there's a few things to check. So theorem, propose and reject algorithm produces a stable matching. Okay, in other words, no unstable pair. It doesn't produce an unstable pair. Okay, so some of these bits of the proof are almost easier to just talk out rather than write out, but I'll at least try to explain a couple parts of it here. So the first question is, does PRA halt? So does this halt? Will it stop? How can we determine that it actually stops? So it stops if we reach a point where each woman is receiving at most 1 proposal. Should we get there, Ethan?
There are a finite number of pairs, and every rejection removes a pair.
Yeah, I'm not sure if everyone heard that. Ethan, your mic's a little quiet, but there's a finite, each list is finite, right? The number of women that you can propose to among the men. And at each day that list is shortening, or we reach the point where each woman gets at most one proposal. So like it's winnowing down the number of options to propose to till eventually, in principle, every list could become 0 and there's no proposals. But certainly you get to a point where there's at most one proposal for each woman, okay? So it halts, I'm just gonna say yes, as lists are finite, right? Because if it doesn't stop, the lists get shorter, and otherwise it stops, right? Once we have a few enough there. Okay, so the number of possible proposals decreases at each day. If it doesn't decrease, then we actually reach the stopping condition. Okay, so now I want to make 2 very simple observations that immediately lead to the fact that every man and every woman are married. So there's no unmarried pair, because that's not part of a stable matching, right? A stable matching is a perfect matching. So every man and every woman should also be married. And at the moment, that's not perfectly clear either. Okay, so the first observation is a woman will marry eventually if she gets a proposal at some point. So as soon as a woman gets a proposal, she's guaranteed to marry, right? Because again, think of the algorithm here. She gets a proposal, and that means that she's got a man she's saying maybe to. And she'll never be in a situation where she doesn't say maybe, because once a man's getting a maybe, he's going to keep asking that same woman until she rejects him, right? He doesn't magically jump up on his list. He's currently proposing to the highest ranked woman that he can, and he'll keep proposing until she either marries him or she rejects him. But if she rejects him, that means she had a higher ranked proposer. So once she's got a man proposing, she'll always have a man proposing, okay? And once you get one, that means that you will eventually marry someone. Maybe not that one, but someone, right? Because you never reject everyone. And at the end, you'll reach a point where you do have one proposing to you, okay? And then the second one is, how does a man not marry? So a man does not marry if he exhausts his list. If every woman rejects him, that's the only way it can happen, right? If every woman rejects him, right? He has a ranked list of all the women, and the only way he can not marry is if each one he proposes to eventually rejects him. These 2 properties together guarantee we get a perfect matching. This implies the propose and reject algorithm produces a perfect matching. I don't claim it's stable yet, that's the next step here, but it does at least marry everyone here, okay? Why? Well, it's simple, it actually just follows immediately from 1 and 2, but suppose it doesn't. So if not, then then if B is unmarried, right? So if we don't produce a perfect matching, it means that there's some woman B who never marries. This means B was never proposed to. But maybe more importantly than that, if B is unmarried, if there's an unmarried woman, what does it tell you about the men? I didn't maybe say this clearly early on. There's as many women as men, right? Like if we don't have that, then of course we can't have this situation. But there are as many women as men. That's sort of implicit in this problem here. So if B is unmarried, then there's some B that's unmarried, and this is already problematic because how did A fail to marry? He was rejected by everyone. In particular, he was rejected by B, which meant that B did get a proposal, which meant B should be married, right? It's an immediate contradiction. If you can just like visualize it too. If B is unmarried, there's some A that's unmarried. Why aren't B and A married? Like, or why didn't they, like there should have been a proposal at least between them. And if that happened, then B would have maybe not married A, but she would have married because she had a proposal, okay? So if B is unmarried, then there exists A unmarried, who had to be rejected by B, which is a contradiction to 1. she would have had a proposal. The only way he gets rejected by B is if he proposed to B, so B should be married. So it does get us a perfect matching, okay? Now, what's more important is this perfect matching stable? And this is actually really simple as well, okay? And this finishes the proof. So is it stable? So if not, let's look at a picture here. That means there's an unstable pair. So here's A and here's B. And it's A and B, this is an unstable pair. So A, B, unstable. That means that they're both married to someone who they do not, they prefer each other to the people they're married to. So A, say, is married to Y, and B is married to X. But B is higher ranked on A's list than Y, and A is higher ranked on B's list compared to X. Okay, so the unstable pair is this one here. All right, so this, if not, we have the following situation here. So A married Y and B married X. So what this means is, Y, if B married X, so if B, Y is in the matching, the perfect matching, so that means that they're married to each other. This implies, wait, no, sorry. BY is not married, it's two women in this model here. A marries Y, sorry. So if A married Y, this implies that A proposed to B and was rejected, right? Because B was higher ranked on A's list. The only way that A ended up proposing to Y is with A was already rejected by B at some earlier day, right? That's you never propose to a lower ranked person unless you've been rejected by everyone above them. So if A prefers B to Y, that means that A was rejected by B. Okay, that can happen absolutely normally in the algorithm, but not in this scenario when B prefers A to X as well, because how did B end up with X? But BX is an edge, which means that, well, no, okay, we don't even need that. We don't even need that, sorry. I mean, that'll be the contradiction, but if B, why would B reject A? Why would that happen? What's the circumstances that allows for that to happen?
It has a better matching.
Yes, exactly. Because so B only rejects A because B had a higher ranked proposer to her at some point. This means B had a higher ranked proposer. Okay, so at the point when A proposed to B in order to get rejected so that he ended up with Y, that meant B also had a proposer with a higher rank than A. Well, then how did she end up with X? Right? I mean, she'll never marry lower than the highest offer that she gets because she always rejects the people lower. So she'll keep saying maybe to this hypothetical person ranked above A. She keeps saying maybe, maybe, maybe. At some point, X proposes to her, but she would have rejected him because she had someone higher. It wasn't A, but it was someone even higher. Okay? But so that's a contradiction. So this means B had a higher than X proposer, who she should have at least said maybe to and rejected X. Okay, she would have rejected X at that point, or eventually, right? X may not have been proposed to her yet, but when X did, she already had a higher ranked proposer, right? If X maybe was proposed to her earlier, that higher ranked guy still eventually proposes to her. Okay? So this situation just simply can't happen. It's very simple. Okay, and that's the end of the proof. So this does produce a perfect matching, and it produces a stable one. And as we saw in the example above, there are multiple stable matchings in principle, but this produces one. Okay. Actually, this is a nice and open question. I do state it in the bottom of the text. Is given a ranked set of preferences, how many stable matchings exist under that ranked set of preferences? We know there's one because PRA will tell us that there's one. But how many do there exist? It's exponential. It's actually open. We like don't know in general. We don't have a good answer to that. Andy, do you have a question?
Are all perfect matchings equal, or is there an optimal perfect matching?
Okay, that's a good question. So you mean among, like, you could put some measure on the perfect matching for, like, so there's definitely multiple stable ones, but you could decide like what's better than another stable matching, right? Like maybe if the average, like, you know, something like man optimal might be something like, oh, the average man, you know, the average rank, like position in the ranked list that the man marry is optimal. You can come up with measures like that, but there's, you know, there's a million things you could do there, and you could just decide. I forget, I told you that this one produces a man optimal perfect matching. I forget what the measure is for man optimal in that case there. It might, I don't think it's average. I think it's just that the least happy man is as happy as you can hope across all of those. It's something like that, right? It's something like, I forget exactly, but actually there's a nice Wikipedia article on this that has some discussion about those issues, which I think is absolutely fascinating. And why it's still of some, maybe not value, but interest to propose this in this old-fashioned style, because I think there's some interesting things going on behind the scenes as well that we don't often talk about in mathematics, right? So, okay, great. So that's all I wanted to say about stable matchings. There are other things that can be said here. There are other algorithms and other ways of doing this, but I want to jump ahead, and we have enough time maybe for one proof in this topic here, and talk about vertex covers, and then give you one big theorem here that's really easy to prove here, okay? So this is still related to matchings, but it moves on from this. Okay, so a vertex cover, this is a simple concept, is a set of vertices that see every edge of the graph. So if I give you a graph, so a vertex cover in G is a set of vertices such that, let's say a set of vertices X, such that every edge of G is incident to a vertex of X. Okay, so you've got this big complicated graph with a bunch of edges, and a vertex cover is just the set of vertices, like in principle all the vertices, but some subset of the vertices, such that every edge is incident to at least one in that set there. So let's just look at a picture here. So we've got a graph here. And let me draw for you a vertex, two different vertex covers. So here's one vertex cover in red, right? If you look at this picture and you examine every single edge, each edge sees one or possibly two red vertices, right? This edge, these three clearly do. This edge does. Oh, actually this edge doesn't. Oh, I made a mistake. Okay, that's fine. This is not a vertex cover. So something that's not a vertex cover is just as illustrative as one that is, because of this edge here. That one's not hit there. But let's do in green, let's do a vertex cover. How about that vertex? That's a pretty valuable one to pick, right? That has a high degree. That's a good starting point. And I think this one here, in green there, that's a vertex cover, right? Oh, no, it's not. No, it's not. No, it's not. We need it. This edge is still not covered here, so let's add this one here. I better check my notes here. I might have made a mistake in my lecture notes as well here. So that was a vertex cover there. Now, usually what we're trying to find is a minimal vertex cover. So if I give you a complicated graph, I want to find a vertex cover using as few vertices as possible. For instance, like I can add in that vertex. That's a vertex cover as well of size 4, but I didn't need that vertex. It was redundant. So there was a smaller one there. And maybe by shifting vertices around, I can get even smaller. In this example, I think I need 3, okay? But in general, finding an algorithm to determine the minimum size vertex cover, that's hard. That's an NP complete problem, an absolute classic that like there's no quick algorithm for solving that as of now. So finding vertex covers is hard, but we can still say things about them. And in a bipartite graph, and this is the theorem I want to give here real quick, there's an important theorem that relates the size of a matching to the size of a vertex cover. Okay, they're closely related in bipartite graphs, and this is a core theorem. We've already seen 2, right? We talked about Menger's theorem and Hall's theorem were 2 examples of these big 6 theorems. This next one, Koenig-Agarwari, is also one of the 6. It's simultaneously equivalent to those as well. And we'll actually use Hall's theorem to prove it. Maybe, I mean, we might only have a sketch of the proof here. Okay. So theorem, this is Koenig-Agarwari theorem. I don't know the year off the top of my head here, but G is bipartite. So we're working in a bipartite graph. Then the max matching size of the max matching is the size of a minimum vertex cover. So what's a max matching? It's just a matching in that bipartite graph that has as many edges as possible, right? There are many different matchings. Hall's theorem tells us whether there's one saturating or not, but this is just how many edges can you pick in a matching, right? Like we can have a bipartite graph like this guy here and say you have, you know, I mean, I don't want to draw in a bunch of edges here, but like this graph here has a matching of size 3 in it, and that's the biggest one that's there. You might have another graph whose max matching is bigger than that. I mean, 3 is the biggest you could hope for because there's only 3 vertices here. Maybe if I add another one here, this one still has max matching size 3, right? The biggest matching I can find in there is 3. And so this says that the size of a maximum matching is equal to the size of a minimum vertex cover in a bipartite graph only. In general, this doesn't hold, but in bipartite graphs it does hold. This is a classic what we call min-max theorem, right? The minimum of something is equal to the maximum of something else. These are common in not just graph theory, but elsewhere. Yeah, I guess I realized like these past few lectures, a few of you took maybe matching theory with Mark last year, I think. And so I'm no doubt you saw this and probably stable matching. So some of this may be familiar to some of you guys already, but that's fine here. Okay, so let's do the proof of this real quick. And we just have a couple minutes, so I'm gonna zip through it a little bit here. So let's call the size of the max matching M. That's the maximum size matching that we have in our graph here. And notice that immediately, oh yeah, so vertex cover needs at least M vertices. That's immediate, because if I have a maximum matching in my graph here, here's the maximum matching, my vertex cover needs to see these edges and all the other edges, but it needs to see these ones for sure. And in a matching, these edges are independent. They don't share any vertices. So if I have a vertex cover, I need to at least capture one of the endpoints of these guys here, no matter what. I might on occasion need to capture both endpoints, but at the very, very minimum, I need to capture one endpoint. So vertex cover's gotta be of size at least M, where M's the biggest matching in the graph there. The question is does the reverse direction hold? And that's what we'll do. We'll actually produce a vertex cover of size at most M, and then that says that the minimum size is exactly M. Okay. Yeah, good. So we actually need a tool in order to solve this. We need what's called the defect Hall's theorem. And proving this is going to end up being one of your homeworks. It's stated as an exercise in the previous thing. You know, you won't have this as homework till next week. It won't be part of the exam homework. But it says the following, that, let me write it this way, that if S minus D is at most the neighborhood of S for all subsets of the vertex set of A. So we have a complete or not a complete, but a bipartite graph with classes A and B. Just think of the model of Hall's theorem. So this is our new condition here. There's this annoying D in here, right? In Hall's theorem, it's just the size of for every set should be at most the size of the neighborhood. Then you have a matching saturating A. If you have this, then, and this is actually an if and only if, but then there exists a matching that saturates size of A minus D vertices of A. Okay, what's D? D is an integer. Okay, so D is greater than or equal to 0. So what's going on with this statement here? This is actually a strengthening of Hall's theorem, because this is, if D equals 0, this is literally Hall's theorem. every subset is bounded above by the neighborhood size, which was the reasonable necessary condition. And then we get a saturating that saturates the size of A minus 0 vertices of A. That just means it saturates all of A. But you can actually strengthen it and say, okay, so I don't pass Hall's condition, but I'm always like, after subtracting 5, I always satisfy Hall's condition, right? So this means neighborhoods could be smaller than S, but they're never more than 5 vertices smaller than S when D equals 5, right? That means that, okay, I can't saturate all of A, but I can saturate all of A minus 5 vertices there. So there's like this clear connection between this and this here. Okay, this is the defect version. So it says that you can actually produce a large matching as long as Hall's condition is maybe not satisfied, but satisfied globally. You're not off by D ever. Then you can guarantee that you can get a large matching within D there, okay? All right, I don't want to spend more time on that because I really want to at least state how the proof goes. So, okay, suppose, oh, wait. So no, there is no matching of size m plus 1 in G, because the maximum was m, we gave it a name. So this means that the defect form of Hall's theorem would fail if this size here were m plus 1, right? Like if so, I mean, this is, you never write it like this, but I'm gonna say if and only if first here. Grammatically, this is monstrous, but anyway, these two are equivalent to each other. So if this fails, if you don't have a matching of this size and this being equal to m minus 1, it means that there exists a set S here that fails this property here. Just like in Hall's, right? If you don't have a matching that saturates A, then there's a bad set S. And that's the same thing here, okay? So there exists an S subset of A such that we have the following, that the neighborhood of S fails to be larger than S minus D. So it fails to be greater than or equal to S minus D. And that's S minus, okay, so this is a little bit awkward here. If m plus 1 equals A minus D, A is the number of vertices in a class. I'm going to call this N. And D is then determined by N and m plus 1. So you have to do a little algebra. It works out to be this. This will be the correct number here. You just have to believe me for now. And this is saying the same as, and just do some algebra here, ns plus n minus size of S is at most m. And now we make one final observation. So this meant that there was a set S that failed the defect form of Hall's condition. And then if I just simplify here things, I have this simplification. Now let's look at our picture. Here's S that failed Hall's, and here's N of S. The edges in this graph live where? Edges go from S to NS, and edges go from, this is A minus S. They could go anywhere from there. But crucially, there's no edge here to S, right? We actually already saw this picture when we proved Hall's theorem. We saw a very similar picture here. There's no edges here. So what it means is that I can make a vertex cover as follows. So every edge incident to A minus S or N of S. So every edge on this, there's no edge here. So every edge is either adjacent to these vertices here or these vertices here, or potentially both. So why don't I take these vertices Oh, that's frustrating. I'm back. All right. Yeah, that's great, right? I like hit 1050 and my computer froze. Anyway, so this is my set. A minus S and NS. That's my vertex cover. And what's the size of those two sets together? It's this. NS plus the size of A minus S. That's the size of those two things sum to at most M. So I found you a vertex cover of size at most M. And that's the end of the proof, right? Because I told you I would do that. I know I rushed through that. I'm sorry, guys. But take a second look at it in the notes if you want to. But that is Koenig-Egger-Varé. And that's pretty easy, although we did use Hall's theorem in disguise there.